So in the last video, we talked about what a matrix multiplication represents. So essentially, it just packetizes nicely a bunch of different dot products. And we talked about the number of dot products that we do is just the number of rows on the left multiplied by the number of columns on the right. And in total, the number of computations or multiplications specifically that we have to do is the number of rows on the left multiplied by something called the inner dimension, which is the shared dimension between the first and the second matrix, and the number of columns in the right matrix. So we talked about like what it does, but we didn't talk about how to actually compute the in a matrix multiplication. So I'm going to do that now. I'm going to make two small matrices, 0, 1, 2, 3, and another matrix, 4, 5, 6, 7. So remember, a matrix multiplication is just all the possible dot products that we can do between pairs of one row vector on the left and one column vector on the right. So the dimension of the output is essentially equal to the number of row vectors we have on the left, so the number of rows. So we would have 2 rows in the output, and the number of columns on the right. So in this case, it's also 2. So we have 2 by 2 as our output. So let's actually show the algorithm, like where I want to show you how the dot products are positioned into the final output. So the way that we look at the where the dot products go is you look at the index on the left. So I'm going to be using 0 indexing like in a programming language. So 0 and 0 for the column. And the output goes into position 0, 0. Okay? So 0, 1, this row vector gets dotted with 4 and 6. So that would be 0 times 4 plus 1 times 6, so 6. And it gets positioned into 0, 0 in the output. So now what you could do is just randomly choose a row vector on the left and a column vector on the right. And you can put the output into its designated position. And you can call that an algorithm, like you performed matrix multiplication. So for example, let's say that I wanted to do 2, 3, I chose randomly, and 5, 7. So this is the row index 1, so the second one, and then 5, 7. So that means that our output goes over here. So what is that output? Well, it's 2 times 5, so 10, plus 3 times 7, 21, so 31. So while you could randomly do this, the more standard way is that we're going to do a walk. So the type of walk we're going to do is we keep the column vector fixed, and we walk through all the possible row vectors until we don't have any rows anymore. Then we go back to the starting row, and then we move our column vector to the right. So in this case, we already did the first one, which computed to 6. So now keep our 4, 6 fixed and move to the next row. So 2 times 4 is 8, plus 3 times 6, which is 18. So our output here would be 26. Now we don't have any more rows, so we move back to the first row, and we move to the next column. So 5 times 0, 0, plus 1 times 7 is 7. And we already did the last one. So now we've just performed a matrix multiplication. So now I want to give you some more details into why we care about these matrix multiplications and what they could possibly represent. So what I'm going to do is I'm going to pull out some high school physics equations. Don't worry about the fact that it's physics. We're not going to be doing any of that in this course. I just wanted some concrete examples. So I'm going to pull out this equation. So our final velocity equals our initial velocity plus our acceleration times time. And I'm going to pull out a different equation, which is our final velocity squared is equal to our initial velocity squared plus 2 times acceleration times our displacement in x. So what I want to do now is I want to construct a neural network diagram from the following equations, and then I want to show you how we can convert that diagram into a matrix multiplication. So let's start by writing our input features. Remember, features are you can think of them as the nodes in our directed graph. So here are some features. So I'm going to make a feature for our initial velocity. And you might be tempted to think that we have two different features, a and t. But if I were to create a feature for a and t, and remember our neural network diagram, we make an output, v, and we make these directed edges, which represent the weights and biases. So the way we interpret this is we multiply all the input features by their respective weights and then add them up, and that's how we produce v. But there's no such way to do that, to be able to make a multiplied by t, right? I mean, there is one way. If we had a weight t and then potentially we had a 0 over here, that technically works. But remember that this is data that is coming from the real world, whereas these are fixed parameters. So that's not going to work in most cases. So what we really need to do is we need to keep a feature that stores the product of a and t, and that's just one feature. Okay, so now let's think about what are our weights. Well, 1 gets multiplied by v0, and 1 gets multiplied by a t. And for consistency, let's make a bias term as well. But we can obviously see that our bias is just 0. But I'm going to add it for completion so that we always have our weights and biases. So now I'm going to make another output. So remember, in our Celsius to Fahrenheit, we just had one output. Now we have two. And I'm going to now draw the features. So v0 squared and a delta x. There's no 2 because that 2 is actually our weight for a delta x. Whoa, what's going on there? Let's fix that. So this would be multiplied by 2, and that would contribute here. And this is times 1. And just like in the other equation, our bias here would be 0. Okay, great. So now let's convert this into a matrix multiplication. So we have two outputs, so let's make a vector that has, well, two outputs, v and v squared. Okay, so we have two outputs, and now we have two different, well, it looks like we have two different dot products here, right? So you have the dot product between these weights and biases, so 1, 1, and 0, with v0, a, t, and 1. And we have this following, the next dot product over here. So somehow we're going to have a matrix multiplication that's going to do two different dot products. Okay, so let's say that I want to make a vector that represents my input. So we need to think about this very, very carefully. What is going to be the dimensionality of this? So let's do a bit of a dimensionality analysis right now. So we have a vector output, so you can think of this in a way as like a 2 by 1 matrix. Okay, so 2 by 1. And remember that when we're doing matrix multiplication, if you have an A-B matrix and a BC matrix, the dimension of the output would be A by C. Okay, so if this is our output, then that means that our A would have to be 2, right? Because we already know that if this is our output, well, A is 2, and C would have to be 1. So we need to construct our inputs in such a way that the first input has 2 rows and the second input has 1 column. Okay, so how are we going to do that? Well, we can see that we have 2 sets here of parameters, this 1, 1, 0, and this 0, 1, 2. So we can think of, like, it makes sense that the parameters are going to have 2 rows in some way. And we can think of the input as one big vector. So remember, vectors, they're just one column, or particularly if this was a column vector. So let's just make a guess right now and say that our B by C matrix is actually just this big vector. So V naught AT 1 V naught squared and A delta X. So this is our vector. Okay, so now we've chosen this to be the right-hand sided matrix, right? So we've chosen that, but we now know B. Because we've decided what this vector is, we now know the number of rows in the right is this inner dimension. So what is our inner dimension? We have 1, 2, 3, 4, 5. So we have an inner dimension of 5. So that means on the left, well, remember, we now know that, so we know that this is 1, we know that this is 5. Because of the fact that these B's need to be the same, this is also 5. And we know that A has to be 2. So let's make a 2 by 5 matrix. We don't necessarily have to populate the values yet, but just make it. So 2 by 5. So we have 2 by 5. And here we have 5 rows and 1 column. And the output of this is V squared. Which is 2 by 1. So now let's think. So what do we need to do? So I guess, say we have a row vector here. We take the dot product between that row vector and this column vector, and the output is V. So what we do in order to figure out that vector is, well, remember, we multiply term by term with the corresponding values on the right. So in the top equation, to produce V, we can see that we need to multiply V naught by 1. So we put 1 here. Same thing for AT, we multiply it by 1. We multiply 1 by 0, as we discussed. And the same thing, see how these features don't contribute at all to the output V. So you can think of also creating some weights over here and assigning these 0. But you can just assume that for A delta X. I just don't want to make this too messy. But just assume that if I don't draw an edge, it's just 0. So in this case, both V naught squared and A delta X will be assigned 0. So now let's do a sanity check. So imagine you do the dot product between this and the column vector. Now this would be 1 times V naught plus 1 times AT plus 0 everything else, and of course it works out to be equal to V. Let's do the same thing for the next equation. So just as we can assume that over here we didn't draw an edge between V naught squared and V, that's a 0. Well, same thing for V naught and V squared. So we're going to put a 0 over here, because 0 times V naught, that makes the V naught contribution to V squared to be 0. Same thing for AT, and there's nothing on the 1, so there's no bias as here either. And then we have 1 times V naught squared and 2 times A delta X. And if you want to just sanity check this dot product again, you'll see that it's identical to the following equation, which is equal to v squared. So I guess what I want you guys to get out of this is that matrix multiplication just represents a lot of different linear equations, and we can use matrix multiplication to store these equations in a very compact way. Okay, great. I think in the next video it would be about time to get to some of the coding, so hope to see you guys there. All right, bye.